Why is Earth bright but space pitch black? The sun pumps out massive amounts of light, yet astronaut photos show nothing but darkness behind them. Today we're solving this cosmic mystery and busting some major misconceptions along the way. Let's dive in. Let's start with the basics, because understanding this mystery requires us to think about light in a way that might surprise you. When you look around right now, you're seeing light that has bounced off objects and traveled to your eyes. That's how vision works. Light hits something, reflects or scatters, and then travels to your eyes so you can see that object. Now here's the key insight. Light itself is invisible. I know that sounds weird, but think about it. You can't see a laser beam unless there's dust or smoke in the air for the light to bounce off of. In a perfectly clean room, that laser beam would be completely invisible until it hits something. The same principle applies to sunlight traveling through space. The sun is absolutely pumping out light in all directions. We're talking about an unimaginable amount of energy streaming through space every second. But here's the thing. Space is mostly empty, and I mean really, really empty. When we say vacuum of space, well, we're talking about a region with incredibly few particles to interact with that light. On Earth, it's a completely different story. Our atmosphere is packed with molecules: nitrogen, oxygen, water vapor, dust particles, and all sorts of other stuff. When sunlight hits our atmosphere, something magical happens called scattering. And the type of scattering that makes our sky blue and our planet bright is called Rayleigh scattering. Picture this. Sunlight coming from our star contains all the colors of the rainbow mixed together, which appears white to our eyes. But when this white light hits the tiny molecules in our atmosphere, something fascinating occurs. The shorter wavelengths, the blues and violets, get bounced around much more than the longer wavelengths like reds and yellows. To put this in perspective, blue light gets scattered about 9 times more than red light. That's why our sky appears blue during the day. All that blue light is getting pinballed around by air molecules coming at us from every direction, creating that beautiful blue dome we see overhead. But here's what's really important for our main question. This scattering doesn't just make the sky blue, it makes our entire planet bright. All that scattered light is bouncing around in our atmosphere, illuminating everything from multiple angles. It's like having millions of tiny mirrors in the air, redirecting sunlight in all directions. That's why even areas in shadow on Earth aren't completely dark. They're being lit up by all this scattered light bouncing around in our atmosphere. Now let's flip the script and talk about space. Remember how I said space is mostly empty? Let me give you some perspective on just how empty we're talking about. In the best vacuum we can create on Earth in our laboratories, there are still about 100,000 particles per cubic centimeter. In interplanetary space, the space between planets in our solar system, there are only about 5 particles per cubic centimeter. And in the vast regions between stars, we're talking about maybe 1 particle per cubic centimeter. This is emptiness on a scale that's almost impossible to comprehend. There's essentially nothing there for light to bounce off of, nothing to scatter that brilliant sunlight streaming through space. So when you look out into space, you're looking into regions where light is traveling in straight lines with virtually nothing to redirect it toward your eyes. Think of it this way. Imagine you're in a huge dark warehouse with a single, incredibly powerful spotlight at one end. If the air in that warehouse is perfectly clean, no dust, no smoke, no particles at all, you won't see the light beam unless you look directly at the spotlight itself. The light is there, traveling through the space, but there's nothing for it to bounce off of to reach your eyes. That's essentially what's happening in space. The sun is like that spotlight, blazing away with incredible intensity. Its light is streaming through space in all directions, but there's virtually nothing out there to scatter it. So unless you're looking directly at the sun, or at something the sun's light is hitting, like a planet, moon, or spacecraft, you see darkness. And this creates a fascinating paradox that confused people for centuries. How can the sun be so bright, yet space looks so dark? The answer is that brightness and darkness aren't really properties of space itself. They're about whether there's something there to interact with light and redirect it to our eyes. Here's another way to think about it. Right now, as you're watching this video, there are radio waves, microwaves, and all sorts of electromagnetic radiation passing through the room around you. But you can't see any of it because there's nothing making it visible to your eyes. Light in space is similar. It's there, it's incredibly intense, but without matter to interact with, it remains invisible to us. Now let's tackle some misconceptions that trip up a lot of people because this topic is full of them. The biggest one I hear all the time is, if there are stars everywhere in space, why don't we see them in astronaut photos? This is a fantastic question that has nothing to do with whether space is dark or light, and everything to do with how cameras work. When Neil Armstrong was photographing Buzz Aldrin on the lunar surface, he had to make a choice about his camera settings. Film cameras, and this applies to digital cameras too, have something called exposure settings. You've got your aperture, which controls how much light gets in, and your shutter speed, which controls how long the camera collects light. Here's the thing. Buzz Aldrin, in his bright white spacesuit, standing on the bright lunar surface with the sun blazing down on him, was incredibly bright. To get a good photo of Buzz, Neil had to use camera settings that would properly expose for that brightness. Fast shutter speed, smaller aperture, settings that would capture Buzz clearly without overexposing the image. But stars are incredibly dim compared to a sunlit astronaut. With those camera settings optimized for bright subjects, the stars simply didn't register on the film. They were too faint to leave an impression during that brief exposure time. It's exactly like trying to take a photo of someone standing next to a campfire at night. If you set your camera to properly expose the person lit by the fire, you won't see the dim stars in the background. But if you set your camera for a long exposure to capture the stars, the person by the fire will be a bright, overexposed blob. And here's the proof that stars are definitely visible in space. Some Apollo astronauts did take longer exposures during photographic experiments, and guess what? You can see stars in those images. They show up as pinpoints of light behind the overexposed fuzzy blobs that are the moon or Earth. Another misconception I want to address is the idea that you need an atmosphere to see stars. That's completely backwards. Astronauts report that stars in space, when they can see them with their eyes, are actually more brilliant and numerous than what we see from Earth. Our atmosphere actually dims and twinkles the starlight. In space, without atmospheric interference, stars appear as steady, brilliant points of light. So let's take a trip to other worlds and see how different atmospheres create completely different sky colors. This is going to blow your mind and really drive home why Earth's atmosphere is so special. Let's start with our moon, which technically isn't a planet but makes a great comparison. The moon has essentially no atmosphere, just an incredibly thin layer of gases that barely qualifies as an atmosphere at all. So what color is the lunar sky? Black. Even during the lunar day, when the sun is blazing overhead, the sky remains black because there's nothing there to scatter the light. It's like our space example, but right on a celestial body's surface. Now let's hop over to Mars, and this is where things get fascinating. Mars does have an atmosphere, but it's radically different from Earth's. First, it's incredibly thin, about 100 times thinner than Earth's atmosphere. Second, it's mostly carbon dioxide instead of nitrogen and oxygen. And third, and this is the key, it's always full of dust. So, what color is the Martian sky? Butterscotch, I'm not kidding. It's a yellowish-brown color that looks exactly like butterscotch candy. And the reason is completely different from why our sky is blue. Remember how I said Earth's sky is blue because small air molecules scatter blue light more than red light? Well, Mars has a permanent haze of dust particles suspended in its thin atmosphere. These dust particles are much larger than the wavelengths of visible light, which changes everything. Instead of preferentially scattering blue light like Earth's tiny air molecules do, these large dust particles on Mars preferentially absorb blue light and scatter the remaining wavelengths, the yellows, browns, and reds. The dust contains iron oxide minerals, basically rust, which gives Mars its reddish appearance and contributes to that butterscotch sky color. Here's something that really drives the point home. If Mars didn't have all that dust in its atmosphere, its sky would actually be blue, just like Earth's, but darker. The carbon dioxide molecules in Mars's thin atmosphere would still scatter blue light more than red light through Rayleigh scattering, but because the atmosphere is so thin, it would be a much darker blue than Earth's sky, similar to what you see if you go to very high altitudes on Earth where the air is thinner. But Mars is never dust-free. The planet experiences massive dust storms that can engulf the entire world, and even during calm periods, there's always fine dust suspended in the air from previous storms. This dust completely dominates the sky color, creating that permanent butterscotch hue. And here's a mind-bending detail. On Mars, sunsets are blue. Yes, you heard that right. While Earth has red sunsets and blue skies, Mars has butterscotch skies and blue sunsets. During Martian sunsets, the sun appears as a bluish disk because the dust in the atmosphere scatters away the reds and yellows, leaving the blues to reach your eyes when you look toward the sun. Let's quickly visit Venus, which is like Earth's evil twin. Venus has an incredibly thick atmosphere, about 90 times denser than Earth's, and it's mostly carbon dioxide with clouds of sulfuric acid. The sky on Venus would appear orange or yellow, and the surface is so dim that it's like being underwater on a cloudy day on Earth. The thick atmosphere scatters and absorbs so much light that very little reaches the surface. These planetary comparisons really highlight how special Earth's atmosphere is. We have just the right thickness, just the right composition, and just the right amount of particles to create our beautiful blue sky and bright, well-lit surface. Now that we understand the basic principles, let's explore some related phenomena that really showcase how atmospheric scattering works. You've probably wondered why sunsets and sunrises are red and orange instead of blue. This is actually the same Rayleigh scattering process we've been talking about, just taken to an extreme. Here's something that might surprise you. The same scattering that makes our sunsets red is happening all the time, even at noon. It's just that when the sun is high overhead, the light doesn't have to travel through as much atmosphere, so less blue light gets scattered away. But that blue light that does get scattered, that's what's creating our blue sky. It's being bounced around in all directions by air molecules coming at us from every part of the sky. This brings us to a really important point about why Earth is so bright compared to space. It's not just that we have an atmosphere, it's that our atmosphere is constantly redistributing light. Instead of light just traveling in straight lines like it does in space, our atmosphere is like having billions of tiny mirrors and prisms, bouncing light around, spreading it out and making sure it reaches places that would otherwise be in shadow. Think about it this way: if you're standing in the shadow of a building on Earth, you can still see perfectly well. That's because light is being scattered by the atmosphere from all directions, illuminating you even though you're not in direct sunlight. But if you were standing in the shadow of a building on the moon, you'd be in almost complete darkness, lit only by light reflecting off the lunar surface. This atmospheric light redistribution is also why photographers talk about golden hour and blue hour. During golden hour, just after sunrise or before sunset, the warm light that makes it through the atmosphere creates beautiful soft lighting. During blue hour, just after sunset, the sky itself becomes a giant soft light source, providing even blue-tinted illumination. And here's a fun fact that connects back to our space discussion: polarization. Remember how I mentioned that bees and other insects can see polarized light? The Rayleigh scattering in our atmosphere doesn't just scatter light, it polarizes it. The degree of polarization is strongest when you look at parts of the sky that are 90 degrees away from the sun. Some photographers use polarizing filters to take advantage of this, darkening skies and reducing reflections. This polarization effect is actually strongest in the ultraviolet part of the spectrum, which is why bees and other insects that can see UV light are so good at navigation. They can see polarization patterns in the sky that are invisible to us, creating a kind of celestial compass that works even on cloudy days. So there you have it, the complete answer to why there's light on Earth, but space is dark. It all comes down to matter. Earth has an atmosphere packed with molecules and particles that scatter sunlight in all directions, creating our bright blue sky world. Space, on the other hand, is mostly empty, so light travels through it without anything to scatter it toward our eyes, creating that deep, dark void we see in photographs. But here's what I find most amazing about all this: the very thing that makes our planet bright and beautiful. Our atmosphere is also what makes life possible. The same molecules that scatter light to create our blue sky are the oxygen we breathe and the nitrogen that makes up most of our air. The same atmospheric processes that give us brilliant sunsets also help regulate our planet's temperature and protect us from harmful radiation. When you look up at a blue sky, you're not just seeing a pretty color, you're seeing evidence of billions of tiny molecular interactions happening every second. You're seeing proof that our planet has the perfect combination of conditions to support life as we know it. And when astronauts look back at Earth from space and see our planet glowing like a blue marble against the black void, they're seeing the visual signature of a living world. The next time you step outside on a bright, sunny day, take a moment to appreciate the incredible physics happening all around you. Every photon of sunlight is being scattered, absorbed, and redirected by our atmosphere in a complex dance that creates the bright, colorful world we live in. And remember that just a few hundred miles above your head, that same sunlight is streaming through the dark emptiness of space, invisible until it hits something like our beautiful, bright planet. The contrast between Earth's brightness and space's darkness isn't just a curious scientific fact. It's a reminder of how special and unique our world is in the cosmic darkness. We're living on a bright island of scattered light in an ocean of invisible energy, and understanding the science behind it makes it even more wonderful. Thanks for joining me on this journey through light, atmosphere, and space. If this video helped you understand something new about our universe, hit that like button and subscribe for more deep dives into the amazing science that surrounds us every day. And let me know in the comments, what other cosmic mysteries would you like to explore? Until next time, keep looking up, and remember, even the darkness of space is full of invisible light, just waiting for something to make it shine.